Okay, in this video we're going to begin Chapter 2. Chapter 2 is all about set theory, okay, and so that's what they call it. Definition, a set is a collection of objects. Could be a collection of numbers, could be a collection of dishes, could be a collection of pencils, could be a collection of three-legged pink elephants, whatever. It's a collection of stuff, okay? Item 1, use set notation to describe the set of counting numbers between 8 and 13. Okay, so between 8 and 13 does not include 8 or 13. So I'm talking about the set containing 9, 10, 11, and 12. Okay, we use capital letters to denote a set, although we can call a set anything we want. But now sometimes certain elements don't belong in certain sets. So for example, a fork doesn't belong in a set of plates. In math, it works the same way. Okay, and that is certain numbers don't belong in certain sets. Okay, so I've got what is our basic sets of numbers that we should know. This is in the book. So the first set of numbers that we should know is the set of natural numbers. Natural numbers are counting numbers, okay, starting at 1. So 1, 2, 3, 4, okay. The ... indicates that the list continues, okay. And then we've got the set of whole numbers. Whole numbers are natural numbers, but we just throw in one more element, which is the element 0. So 0, 1, 2, 3, 4, 5, okay, etc. And then there's the set of integers, okay. Integers are whole numbers, and then they're negatives. Okay, so 0, 1, 2, 3, 4, etc. Also -1, -2, -3, -4, etc. I want the ... going on both directions there to indicate that the list continues in that fashion in both directions. Okay, the positive and the negative direction. We have the rational numbers. Rational numbers are just fancy words for saying that you're talking about fractions. Okay, so all numbers that are fractions are called rational numbers. And then we've got irrational numbers. An irrational number is a number that is not a fraction. Okay, so like the square root of 2, that's not a fraction. Or pi, that's not a fraction. Okay. Real numbers, okay, any number that is rational or irrational is called a real number. A real number is basically any number that you've ever seen, except if you've taken Math 115 where you talk about complex numbers. Okay, you guys won't need to know complex numbers in this course, but in other courses you do need to know those. Okay, so these are our basic sets of numbers here, and number 2, are the following numbers rational numbers? Okay. Well, a rational number, again, is any number that's a fraction. Okay, so part A, when I say 3/4, yeah, that's a fraction. Okay, now a fraction can mean that the numerator or denominator is an integer. Okay, an integer could be positive or negative. Okay, so when I say -5/17, yeah, that's a rational number. Okay, 3 is a rational number, so any integer is a rational number because 3 is the same as 3 over 1. Okay, and of course I can do that to any integer that I want. Okay, I just throw 1 in the denominator, boom, there's my rational number. Sometimes rational numbers are expressed in decimal form, so 0.25, that's the same as 1/4. Yeah, that's a rational number. 0.444, the infinite decimal. Okay, by the way, a decimal that stops or repeats is a rational number. Okay, so this one repeats 4s. That one would be a rational number. Okay, and if you type in 4 divided by 9, there it is. Okay, so problem 3. Are the following numbers irrational numbers? Okay, pi is an example of an irrational number. Okay, because there's no way to write pi in fractional form. Okay, so that would be irrational. The square root of 2, that's the same thing. That's an irrational number. There's no way to write the square root of 2 in fractional form. Okay? Same with the square root of 3. There's no way to rewrite square root of 3 in fractional form, so that's irrational. The square root of 4, that's same as 2, and 2 is a rational number, okay, just like 3 is a rational number. So all I do is throw a 1 in the denominator, and I've got my rational number form there, so 2 over 1. So I'm not just picking any square root here, okay, some work, some don't. How about 0.010110111011110, okay? That would be an example of an irrational number. And an irrational number is a decimal that does not stop or does not repeat. Okay, so this one does not stop, which is indicated by the ... does not repeat. So there's no section where you're going to say like 010 ever again in this infinite decimal. Okay, or 0110. You're never going to see that ever again. Okay, so that would be an example of a rational number. Okay. Definition: the number of different elements in a set A, which is denoted by n of A, is called the cardinality of A. Okay, so we call this the cardinality of A. Problem 4, what is the cardinality of A for set A, which is given by the set containing 1, 4, 9, 16, 25, 36, and 49? So how many different elements are listed there? Well, there's 1, 2, 3, 4, 5, 6, 7. Okay, so the cardinality of A would be 7. Problem 5, what is the cardinality of M for the set M, which is given by the set 2, 2 again, 5, 5 again, and 7? Okay, so the number of different elements, different is a key word there, so that'd be 3. Okay, this is exactly the same thing as the set containing 2, 5, and 7. You see, with sets, I can repeat an element as many times as I want to. Why I would do that, I don't know. Okay, but I could if I wanted to. So if I wanted to rewrite, 36, 23 times, I could do that. It'd still be a set with 7 different elements in it. Okay, different is a key word. Problem 6. What is the cardinality of C for the set C, which is given by the set containing 0, 1, 2, 3, 4, etc., all up to 500? Okay, so there's 501 different elements listed. Okay, it'd be 500 elements if I were starting at 1, and just using the counting number starting at 1, but I'm not starting at 1, I'm starting at 0. So I got to make sure I count 0, the 501 different elements. Okay. Problem 7, what is the cardinality of K for the set K equals the set containing 7, 8, 9, all up to 16? Okay, so what some students will do, and they'll mess this up, is they'll say, oh, well, 16 minus 7 is 9. So there's 9 elements in the set. Okay, you don't want to look at the problem like that. Okay, so if we go 7, 8, 9, 10, that's 4 elements, okay, 11, 12, 13, 14, 15, 16, that'd be 10 elements there. Okay, so I would have had a wrong answer if I just would have said 16 minus 7 is 9. Okay. By the way, I would have had a wrong answer up here if I would have said 500 minus 0 is 500. Okay, so that's not the way that you want to look at the cardinality of a set. It's not just a quick subtraction problem. Okay. Definition: the set containing no elements is called the empty set. The symbols used to represent the empty set are this symbol and this symbol, a set with nothing in it. As a note, make sure that you don't write the empty set as the set containing the empty set. Okay, this would representing a set containing one element, the one element being the empty set. Okay, so this and this mean the empty set. This does not mean the empty set. Problem 8, what is the cardinality of the empty set? Well, the empty set contains no elements. So the cardinality would be 0. Okay. Problem 9. So sets can be described in at least 3 of the following ways. A word description, the listing method, and using set builder notation. Okay, and I'll show you an example of each one. So part A, write down 2 sets using a word description. Okay, word description, of course, is where I have the set brackets, and I just write out in words what I'm talking about. So when I say the set of all rational and irrational numbers, well, that's one way to describe the set of real numbers, right? Which I've already got written there. Okay. The set of all U.S. states, so rather than listing out all 50 states, if I just say the set containing all U.S. states, that's the same thing. Okay. Of course, less writing there. Part B, write down 2 sets using the listing method. Okay, so the listing method is just where I list the elements that I'm talking about. So when I say the set containing 2, 4, 6, and 8, the order of the elements, by the way, does not matter in a set. So I could say the set containing 6, 4, 2, and 8. Okay, it's same thing. Just make sure that you've got all of them listed there that you want. The set containing lowercase a, lowercase b, lowercase c, etc. up to lowercase z would be another set where I'm just listing the elements. Okay. And by the way, when I say listing, you can use the ... That's okay. Okay. If there's many things to list, well, who's going to take the time to list so many elements if there's so many to list there? Okay. So the ... is a preferred symbol to use if you're using a pattern. Okay. Part C, write down 2 sets using set builder notation. Okay, so set builder notation is where I start off by writing the set of all x, and then this vertical bar that you see right by the x means the phrase such that. Okay, so the way that I'd read this is the set of all x such that, and then I just describe what's happening with x. Okay, so suppose that x is an even natural number less than 10. Okay, or the set of all x such that x is greater than 0, but x is not 1. Okay, that would be an example of where I'm using set builder notation. Okay, so these are the 3 methods used to describe a set. Make sure that you know those. Problem 10. We'll look at problem 10 here. Match each set in group 1 with the appropriate description in group 2. Okay, so in group 1, I have the set, and then group 2, I'm using a word description to indicate the set. Let's see. Problem 1, I got the set containing 1, 3, 5, 7, and 9. Well, if I scan group 2 here, okay, I'm looking at odd positive integers, and they're less than 10, right? So F would be the answer to problem 1. Okay, problem 2. The set of all x such that x is an integer between 4 and 5. Okay, I'm using set builder notation. The set of all x such that, by the way, if I don't write the set of all x such that, then this is no different than using a word description. Okay, so the set of all x such that is actually a key part of what you need to use to write set builder notation. Well, now between 4 and 5 does not mean I'm including 4 and 5. Okay, there is no integer between 4 and 5. So G, the empty set, is what I'd have there. Okay. Problem 3. Okay, so let's see. Looks like I'm working with negative integers. So negative 1, negative 2, negative 3, etc. Okay, of course the ... means I'm going to indicate trend going in the negative direction there. Okay, so that'd be E. Problem 4. Let's see, -5, -3, -1, 1, 3, 5, etc. I'm working with the D, the set of all odd integers. Okay, so I've only got odd integers listed here. Of course, I got the dot, dot, dot in both directions. There's the list continues in that trend. Problem 5. So I got the set containing 2, 4, 8, 16, 32. Let's see here. That'd be the set of the least 5, or the 5 least positive integer powers of 2. Okay, so in other words, 2 to the first is 2, 2 squared is 4, 2 cubed, 2 times 2 times 2 is 8, 2 to the 4th power, 2 times 2 times 2 times 2 gives me 16, 2 to the 5th power is 32. Okay, so B, I'd say. Problem 6. Okay, problem 6 is where I'm working with even integers. Okay, so that's going to be A, the set of all even integers. 0 is an even number. Okay, so an even number is one that you multiply by 2, and so 0 times anything is 0, right? So okay, problem 7 there. You got the set containing 2, 4, 6, 8, and 10. That's going to be H, the set of the 5 least positive integer multiples of 2. Okay, so in other words, what I mean there is like 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. Okay, and then C is going to go with 8. So 8 is the set of even positive integers less than 10. By the way, in 8, so here's one way that I could have wrote down the set of all x, such that x is an even natural number less than 10. Well, that's the same thing here. So there's 2, 4, 6, 8. Okay, but if I say the set of even positive integer powers, the set of even positive integers less than 10. Okay, a positive integer is the same thing as an even natural, or is a natural number. Okay, so there's a couple of different ways that I can say this, and of course, I've got the same set written up here, right? So if I were to use the listing method. Okay, and we'll go ahead and stop right there.